happy to introduce Armin Fohler from LTM Linz. He or they at LTM Linz also work closely together with, for example, Astrid Bechstein, who presented yesterday, and a lot of other people from Linz and Joachim's former team, and it's like a kind of also already long-time users of ngSolve, NetGen, building application simulations for electrical machines. And thank you for having you here.
Thank you for the introduction. I will give you a short insight how we are using and where we're using ngSolve in our daily applications. So in general, as Christopher said, I'm from the Linz Center of Mechatronics, and I will give first a short overview what are typical projects or what is our field of work, and then I will go into more detail where we can apply some simulations from ngSolve. First, I'm employed in the area electrical drives, and our team is more or less divided, or not divided, but part of our team is working on power electronics and custom sensors, and the other part is working on electrical machine design. And here we see a first application, and I picked this because, in my opinion, it's quite let's say unusual field, because if you think about electrical machines, you think more or less about generators and motors and so on. But this is an hearing implant, so this is called bone bridge, and the idea is that persons who are deaf because they have some problem in the middle ear, but their cochlea is still functional, we together with the company designed a device that makes it possible to implant it in the skull, and with this you can use the bone conduction, and they can hear again. So although this part of the ear doesn't work anymore, they still receive the sound from outside by this device. The second one is a bit more well known. So this is a hydro generator. This is quite a big machine, so it's, I would say, man's height. And an interesting thing about these generators are all of them has to be custom made. So you can't have a generator and use them in every power plant you want, but you have to take into account how many water you have, the water pressure, and so on. And the field, I would say, we are working the most are electrical motors. And from there we have very small devices, so for example for controlling of valves, and very recently we had a project for a ship motor. So this is a electrical Voith-Schneider propeller, and they are using it, for example, for offshore maintenance of wind power plant. For the simulation and for the optimization, we are developing our own tool, which is called SimSpace, and I will give, and this is the link to ngSolve more or less, because in our own simulation device we built interfaces to other simulation tools, for example HOT and ANSYS and FEM, and also now ngSolve, and also we have links to CAD software. Our simulation models and also the geometry models are in what we call the component space. So if you want to have a complex simulation or optimization workflow, you just plug in all the components you want or you need into your simulation workflow, and then you can go to our cluster and compute everything. Now I want to go into more details about the applications for ngSolve. In general, most of the electrical machines we are developing or we are optimizing are radial flux machines, which means that most of the flux goes into radial direction, which means it's feasible to have a 2D simulation. As you see, so the inner part here is the rotor, and the outer part is the stator. In between you have here the air gap. In the rotor you have the magnets with a certain magnetization direction, and this goes if you are building a variational formulation on the right hand side. And in the stator you have the winding, so these colored slots are depicting the winding scheme of this electrical machine, and this is also a source on the right hand side of your PDE. Gray material is nonlinear material, so electrical steel. Yeah. And there are certain aspects you cannot cover in 2D, so you need 3D simulations. And for this we are using ngSolve. And for example, and I will show this how we do it in our simulations. For example, magnet losses you cannot you cannot cover in a good way in 2D, because the magnets they span in the axial direction the whole rotor. So you have eddy currents there, and you want to cover them also. And end winding effects I will come in the end if I have time. The second application are axial flux machines, and those are electrical machines that you really can't, or I mean, there are some special cases where you can make a model in 2D, but in general you will have to simulate it in 3D. And you see here, this is a special case. So here you have two stators. So this is on the right side, the stator 1 and the stator 2, and in between you have the rotor. This orange, brownish domains are the coils. The gray ones is once again electrical steel, and here attached to the rotor are the magnets. So in blue and red it also shows how the magnetization direction looks like. So I want to start with the magnet loss estimation, and it's an estimation because we don't want to simulate the full eddy current problem, but if you are at this stage, so you have this formulation, then it was not our idea, because this is already covered in some publications. You take normally you have to simulate it time dependently, but if you say, okay, I want to freeze the B field, then you can just look at it as a source. And the idea is basically you make a 2D simulation, in our case in FEM42, and then we export the B field, in this case in the magnets, and also the mesh, and then we can calculate, because this is the rotor is rotating, and you have here the change of the B field with respect to time. So you can calculate this dB dt for every mesh element in the magnet, and in the next step you extrude the mesh from 2D to 3D, and then you solve this formulation by so you have a curl-curl problem, and but the right hand side is what you plug in from the 2D simulation. We made tests if the approximation was good enough, because what you miss is you have some you don't recover the back influence of so normally this time dependency reduces the losses, so you will overestimate your losses. And it depends how much you overestimate, if this is good enough, because it's better to overestimate the loss than you underestimate, clearly. And for example, we made this for this is a benchmark project, so this is the Toyota Prius motor, and for this, so for RPM 1800, this sigma and the magnet length from 84 millimeters. We compared this with the Maxwell simulation and this 2D/3 decoupling, and we got, I mean, it's not aligning, so we have a difference, but in this case it was acceptable. We also did this testing for other machines, and they were well enough that we can use it in an optimization, because sometimes in optimization you're only interested in is the motor performing better than the other or not. And in the end you will have maybe anyhow make a simulation in time which is time dependent. Some additional features of this magnet loss simulation: you can also have a segmentation in X and Y plane, which reduces your eddy current losses. And there is also an approach from, I think it was introduced by Bomatec, where you don't segment the motor, but it's called a snake line. So they make a cut into the magnet, which also reduces the eddy currents in a similar way than if you would segment it, and it's easier to manufacture. Okay, those are pictures how this would look like then so these are V-shaped magnets, as you have seen in the Prius motor, and in this case the snake line is a bit, you have more snake lines than in the example before. Here are some references for this approach. And next I want to come to the axial flux machine. I already gave a bit overview how the geometry looks like. I started this with CSG geometry, and I haven't yet changed to the OCC framework, but I saw that this is quite nice, and I think also some problems I had with the CSG formulation will be maybe solved in the new framework. So I put on the left side how this looks in the real world, and on the right side how this would look like as a model. So these parts are the magnets, and there we have the rotor yoke, and this is similar here. I mean, this is a bit of a different geometry, but I think you get the idea how the rotors for axial flux machines would look like. And a bit more complicated is the stator. So you see here the coils, and this stator has no flux collectors. Flux collectors are so these plates here are called flux collectors, and most of the axial flux machines have those flux collectors, but not all of them. Yeah, and here these parts are the coils, as you see also here, and there we have the stator yoke. Now, since if you make a mesh from the whole geometry, you end up with possibly a large number of degrees of freedom, and because of this we are interested in sector simulation. And there we face the problem that if you rotate the device, then the rotor gets outside of the stator, so you have to think about how you tackle this. And on an early stage we already decided we will use some domain decomposition approach, and this was already done in the paper by Karl Holos and Joachim Schöberl and others. The Nietzsche type motoring method, and the idea is you have the rotor and the stator, and in between you introduce a new interface, and then you couple your degrees of freedom from the rotor interface to the stator interface via this interface gamma. And just a short idea how this can be done. So here you have the variational formulation from integration by parts, and then you add terms. And those terms you add, for example, this lambda and the psi, they live on the interface. but they don't change the problem. So you still have a consistent problem because the lambda is the representation of u on the interface, and so this term and this term cancels if you have the exact solution, and this is due to the normal derivative. So this also cancels out this term. The problem is, as is also stated in the paper, you will over-penalize gradient fields for small kappa, and on the next slide I just put in the whole formula that was given in the paper. I will not go into detail, but just to give you the correct semi-linear form, which was implemented in this case by Astrid Pechstein. And here you have the linear form as I talked about before. You have the J, this is the current density which you have in the winding, and you have the Mx, which is the magnetization in this case of the rotor. What is also nice about this function on the interface, Astrid proposed that we use some periodic functions, because if you shift the rotor outside of the stator, then it's easier to evaluate the resulting functions on the interface. So what is interesting for the post-processing, we're interested in linked fluxes. This is, for example, so I will go a bit more into details for electrical machines, because if you're simulating an electrical machine, you have to perform first a no-load simulation where you don't have currents in the coil, and then from this you can calculate the linked fluxes and the torque, and from the linked fluxes you can get a reference current for your load simulations. And then in the load simulation, this is called a DQ grid. So you make quite many simulations with different currents in the stator, and you then end up for each of the load points with, for example, here for the torque, for each of the load points you have a certain torque. And then we're using RBF interpolation models, and then you can recover from these load points, you can recover steps in between. So normally this DQ grid is not what you want in the end as certain load points, but you need something to compute in between. And also for the axial flux machine, loss calculation is also essential for iron losses, copper losses, and also the magnet losses. But they are, they are implemented, but I didn't test it yet. So here for the reference, and the last, so this was just, if you have time we can cover it, but it just takes some 2 minutes or something like this. Okay. So I'm jumping back to the idea if you are making a 2D simulation and what effects you cannot cover. And for example, here you have the end winding, and as you may imagine, you can't cover all the effects from this end winding for a 2D simulation because this is simply not covered. But there are also quite interesting or important effects. And for this, we tried a reduced model. So you're just taking the copper yoke, and then this is, for example, a toroid winding. This is for this application a quite simple winding. And then you can simulate here the windings and, for example, winding inductances or also losses in the end winding. And yeah, this sums it up. And yeah, acknowledgement. We are also funded by so we are a COMET K2 center, and we are also funded by Austrian federal government and from Upper Austria. So thank you for your attention.
Thank you very much. Are there any questions? Yeah.
So the main part of the motor you're doing with a 2D model, more or less, and just extrude in 3D. But for the end parts, 3D meshes are relevant.
Yes.
What about doing the whole thing in 3D with very long elements over the main part, that you have only a 2D plus discretization as the main part, maybe second, third order?
I mean, we can do it in principle, but I think it's just a question of how time-consuming it is. Now our models are all 2D if it's feasible to calculate in 2D.
2D plus, so 2D stretched is not more.
You mind
time-consuming than
prism mesh or
yeah,
okay?
very anisotropic elements.
Mm-hmm.
And then you have
Yeah, the only thing that maybe contradicts this, in most of the motors you need skewing, and so in this case we have models where we use discrete skewing, but yeah, maybe it's also possible to make it in 3D.
But yeah.
Okay, thank you.
Okay.
Yeah. I think you will also be. Are you also here tomorrow or
Yes.
today? So yeah, then there is plenty of room for discussions. And thank you for your presentation.
Thank you.